is Mark Doley, and I'm going to present the second problem of three concerning work and energy. And this time we're going to work with the combined Newton's second law and work and energy. And doing the problem this way, it shows you where work and energy comes from in a way. It's very similar to the part one, the very general form that I did. This is just going to be an example with some numbers. So it's the same problem that we've been doing. We have our two blocks on inclined planes connected by a pulley. One plane is at 45 degrees, one is at 30. The blocks weigh 50 pounds. Coefficient of kinetic friction is 0.05. The blocks are initially at rest, and we need to find the velocity after the blocks move 1 foot. The method that we're going to use is F equals mv dv dx, and this is it's equal to acceleration by it's a couple steps removed from acceleration, just using the idea that acceleration equals dv dt and that velocity equals dx dt. And doing a little bit of algebra, you can find out that acceleration also equals v dv dx. And our unknowns are going to be our tension in the cable, and the velocity of each block after it moves 1 foot. The relationships that we're going to be able to find, we're going to be able to find one relationship from block A using this sum of the forces equals the mass times the acceleration, and block 2, sum of the forces equals the mass times the acceleration. And we know from our cable that VA is going to equal VB, and to simplify everything, we're going to say that it is also equal to VF. And so we have our free body of block A. Again, I just drew the inclined plane at 45 degrees. I brought the weight coming straight down, the normal coming up perpendicular to the x-axis. We have our motion. I've decided our motion is going to come down the plane, and so our friction is going to go up the plane, and our tension is going to be going up the plane. And that is all equal to the mass times the acceleration. And you don't need to worry about the sign of the acceleration, because when you integrate, the sign is going to come out, and you'll be able to see that. It's going to be when you plug in for your initial and final positions that it's going to determine the sign. So you don't even have to concern yourself with that. So some of the forces we have: negative W, the weight in the x direction is going to be coming down like this. We have our tension going up. We have our friction going positive. And you're going to have to solve for the friction and the weight in the x direction. I just didn't have room to put it up. And so once you enter in all the numbers that you can, you're going to bring this. There should be a dx here, because you're going to bring the dx over. So that's going to be here. So we're going to be integrating in x from the initial x position to the final x position, and then so it's going to be you're going to integrate t minus 33.585 from the initial x position to the final x position, and you're going to be integrating 1.55 v times dv from the initial velocity to the final velocity. And they're both very simple integrations, and so we're going to let the xf equal -1. Since we're choosing our acceleration to go this way, and this is positive x, it's going to start at position 0, and it's going to end at some position -1. So let xf equal -1, let initial x equal 0, and initial velocity equal 0. And so we're gonna, once we integrate and plug in for our initial and final conditions, we come up with negative t plus 33.585 equals 1.55 times the velocity divided by 2. Okay, so I know that we have a little bit of glare on this board, but hopefully I'll be able to put up some bubbles so you'll be able to see the numbers. Anyway, we're on block B now. We're trying to develop our second relationship. And with block B, it's a very similar free body. I draw the inclined plane at 30 degrees. We have our positive x up here. So we have our normal coming up perpendicular to the inclined plane. We have our weight coming straight down, 30 degrees off the y-axis. We have our tension going up and our friction going down because we think our block is moving up the plane, being pulled from the other block. And that's going to equal the mass of block B times the acceleration. And so some of the forces, weight in the x direction plus friction. So weight in the x direction, friction, tension equals friction minus tension. Oh, I'm sorry, this is negative x here. Negative x. This is positive x. That's very important. Equals mass times acceleration. And again, we're gonna bring the dx over. And we're going to integrate 27.165 plus t from our initial position to our final position. Again, letting our final position equal -1. Integrate, substitute in for x, and we get -27.165 plus our tension equals 1.55 velocity squared over 2. For the previous relation, I did not put velocity squared, so you're going to have to go back and take a look at that. So solving, now we have two relationships we can solve for B and T, and I wrote out the two relationships. You can go through and solve for T and then substitute in, or solve for BF squared and substitute in, but you should come up with tension equals 30.38 pounds. And the final velocity equals plus or minus 2.03 feet per second. And so our final answer, VA is going to equal 2.03 feet per second, and we have the direction down the inclined plane. And we have VB equals 2.03 feet per second, and that's going to be going up the inclined plane at 30 degrees. Thank you very much. Hello?
Hey, Kate. Why?